Namaste and welcome back to yet another lecture on linear algebra through geometry. In the last lecture we looked at reflection of a vector in 3-dimensional space about a plane passing through the origin and orthogonal to another vector, and we also looked at the idea of shear transformations. We in fact looked at the application of shears in solving a system of equations where we just made a passing remark saying that okay, in order to clear the elements below the pivot elements, we use which is basically what we do in Gauss elimination method for solving system of equations. We can use shear matrix. So that is what we discussed in the last class, and when we wound up the class we were actually we had a question in mind, like how does rotation happen in 3 dimension, like what is it to say a rotation transformation in 3D, and that will be the focus of this particular lecture. So we are going to look at rotation transformation in 3D. Rotations in 3D. Now let us again revisit our rotation in through 2D. So we will look at rotation in 2D. We'll just try to recall. We said that the matrix R theta, which is given by this cos theta sin theta minus sin theta cos theta, rotates any vector or rotates every vector by an angle theta in the counterclockwise direction. This is what we saw, by an angle theta in the counterclockwise direction. And recall that we also did that if we want to do let us say we have this 2D space, so where I have this vector and I want to rotate this vector, let us say by an angle theta counterclockwise direction. So I am going to rotate, this is going to be the new vector, and then I am going to rotate this new vector by say another angle, let us say phi. The total the total angle that that you have is basically from this point x to, let us say this is x prime and x double prime. So we have actually gone through an angle of theta plus phi in the counterclockwise direction to go from the original point x to the point x double dash. This is exactly what we have. So now what we are going to do is in that case we figured out that okay, let us look at this. The first thing that we have is r theta of a vector x, which is nothing but, let us say, cos theta sin theta minus sin theta cos theta of, let us say, a vector x1 comma x2. Now what did that give me? That actually gave me the following, gave me x1 cos theta minus x2 sin theta and x1 sin theta plus x2 cos theta. This is what we had, and now what we want to do, this is the vector which is basically equal to the x prime vector. Now what we want is from x prime vector we want to go to this x2 prime vector, which is basically by rotating this vector x prime by another angle phi. So let us see what happens to that. So I want to now look at r phi, which is nothing but again cos phi sin phi minus sin phi cos phi. So what are we going to do? I am going to get this vector v double prime, which is nothing but r phi of v prime, r phi of this v prime vector, which is nothing but cos phi sin phi minus sin phi cos phi of, we already had this is nothing but x cos theta, x1 cos theta plus x2 sin theta minus x1 sin theta plus x2, let's just write that, x1 cos theta minus x2 sin theta, x1 sin theta minus x2 cos theta. So x1, let's do this, x1 cos theta minus x2 sin theta then we have x1 sin theta plus x2 cos theta. So what do we basically get here? We get x1 cos theta cos phi, right, cos theta cos phi into, okay, let me do that. We have cos phi into x1 cos theta minus x2 sin theta minus sin phi into x1 sin theta plus x2 cos theta, and the second component is sin phi into x1 cos theta minus x2 sin theta plus cos phi into x1 sin theta plus x2 cos theta. This is what we have. So if we expand and we get this, we get x1 cos theta cos phi minus x2 sin theta cos phi, right, minus x1 sin theta sin phi minus x2 cos theta sin phi. Similarly, we get here as x1 cos theta sin phi, x1 cos theta sin phi minus x2 sin theta sin phi plus x1 sin theta cos phi plus x2 cos theta cos phi. Now, if you look at the term corresponding to x1, you get cos theta cos phi minus sin theta sin phi, and then corresponding to x2 you see it is sin theta cos phi and cos theta sin phi, which is actually the expansion of cos of theta plus phi and sin of theta plus phi. So we have that. So we are going to have v double prime is basically this, we are going to have cos theta cos phi minus sin theta sin phi and what are we going to have here? X2 is going to be sin theta cos phi plus cos theta sin phi, there is a negative. So I am going to write minus sin theta cos phi plus cos theta, okay, let me write this, plus cos theta sin phi, and we are going to have again x 1 cos theta sin phi plus x 1 sin theta cos phi. So, we have cos theta sin phi plus sin theta cos phi, and here what are we going to have? X 2 we are going to have cos theta cos phi minus sin theta sin phi, cos theta cos phi minus sin theta sin phi into x 1 x 2. We see something interesting happening here. This is nothing but cos of theta plus phi, cos of theta plus phi minus sin of theta plus phi sin of theta plus phi cos of theta plus phi. X 1 x 2. So, how did we get our V double prime? V double prime was basically I applied r theta onto x 1 x 2, this vector, okay. I will change this, I think we will change this to V prime, V double prime and so on. So, let me call this as V prime, V prime, V double prime, and let me call this as, okay, let me call this as V prime, and let me call that as V double prime, that is fine. So, what we get V double prime is r theta of the effect of r theta on x 1 x 2, and the resulting vector I am going to transform using r phi. So, what did we get? Basically V double prime was basically r of theta plus phi, that is the matrix that we get here. This corresponds to r theta plus phi. So, what we see is if you want to rotate a vector by an angle theta and then by an angle phi, it is equivalent to rotating it by a total angle which is theta plus phi. Now, incidentally we can see that r theta plus phi, that means applying r theta first and then apply r phi next, is the same as r phi applying r phi first and then r theta next, which implies r theta into r phi is equal to r phi into r theta, which is the same as r theta plus phi. That means we see that the rotation matrix, it is of the form AB is equal to BA. So, we say that the rotation matrix in 2D, rotation in 2D is a commutative operation, is commutative. Right, that is what we have. That means we have AB, the product of two matrices AB is equal to BA. So, where A and B are two matrices of, and then it allows for the matrix multiplication, is that okay. So, then we get AB is equal to BA, where let us say in our case wherever we have taken 2 by 2. So, this is basically A 2 by 2, B 2 by 2 is equal to B 2 by 2, A 2 by 2, if and only if A is equal to, okay, let me not write, if let us say for A is equal to r theta, A is equal to r theta and B is equal to r phi, right. So, it is commutative. Now, let us look at what happens in 3D. In 3 dimension, whatever we have seen right now in 2 dimension is basically the rotation that is happening in a plane. Now, what we want to do is we want to look at rotation in 3 dimensions. So, how does that work out? So, rotation in 3D. rotation in 3D, if you see, we can actually do this. It's the same thing that we have done in rotation in 2D, where in which what we are going to say is the rotation is going to happen in only one plane. It's going to happen in a plane, and your I mean, when if you want to look at the second rotation, there is a problem. We look at, okay, we could actually do the rotation about a specific axis, that means in one plane, and you want to change the rotation to you want the rotation to happen in a different plane, then you get into a different problem. So, we will see what that is. Okay. For looking at rotation in 3D, let us list out the following thing. So, I am going to take rotation by an angle theta about, let us say, the E1 axis or the x1 axis. So, in which case what is going to be r theta. That means, if you curl your fingers, this is the axis. See, if you look at this, if you curl your fingers, this is the axis about which I am going to rotate, and the rotation is going to happen now in x2 x3 plane, right. So, that is what I am going to look at. So, this is going to be rotation that is going to happen in x2 x3 plane, which means my x1 component is fixed. So, how is this going to look like? I am going to call this as rotation theta about, let us say, E1 axis, to ensure that it is about the E1 axis. So, what am I going to do? I am going to have this matrix which is going to do the following. The first component is fixed, it does not change, right. The first component is fixed, it does not change, whereas the second two component is where basically it is on the it is along the x2 x3 plane, and that is where the rotation is going to happen. So, I am going to do this cos theta sin theta minus sin theta and cos theta. So, what does this say? This says that, look, my one of the axis is fixed and I am going to rotate about that particular axis in a plane. That plane is basically, in this case we are going to look at the x2 x3 plane, right. Similarly, I can have for the other two rotation about the other two axes also. I can take r theta about, let us say, the E2 axis, where I am going to write this as r theta about E2, in which case the second coordinate is fixed and we are going to rotate in x1 x3 plane. So, in which case this is going to be the following: 0 1 0 0 1 0. So, now you take this as cos theta sin theta minus sin theta cos theta. Now, we can easily figure out what is it going to be the rotation about the E3 axis. When I say about E3 r theta about E1 axis, E2 axis, E3 axis, it simply means rotation about the reference axis, the three reference axes that you have. So, r theta about E3 axis is basically given by rotation about E3. The third component is fixed in this case. So, I am going to have 0 0 1 and this row and that column is fixed. Now, I am going to rotate in x1 x2 plane. So, this is going to be cos theta sin theta minus sin theta cos theta. Is that clear? This is not something new to us. We have seen this happening. Look, I mean, if you are able to look into the ceiling where you fix the fan is basically fixed at some height and then the rotation is happening in a plane. This is also something that you would see in your helicopter, where the fans rotate at some particular height, and that is exactly what we are seeing here. One of the component is fixed and therefore, the rotation is happening in the plane determined by the other two reference vectors. They may, namely, I mean, if its rotation is going to be around E1 axis, you are going to say that the rotation is now going to happen in E2 E3 plane, right. That is what it is. Now, there is a problem here. What is the problem? Okay, before we even get into the problem, let us look at something interesting here. What happens to the, we were always worried about how does the rotation affect. In fact, in 2D we were looking at how rotation alters the area. We said that rotation preserves the area, preserves every metric and all those things we have seen in case of rotation in 2D. Now, what we need to do is we need to check if that happens here. Now, you can very clearly see that all the vectors that you have, the column vectors, if you see, they are all of unit length, they are all unit length. If you look at this column that I have marked here 1 0 0, that is of length 1. If you look at the second column, this is going to be square root of cos square theta plus sin square theta. So, the length is going to be 1. Here also it is going to be square root of cos square theta plus sin square theta, the length is going to be 1. And what we interestingly see is each of these columns are basically orthogonal to every other column, and we therefore we had last time when we did 2D, we said that rotation is going to preserve area, preserve length and all those things. The same thing happens in this case too, right. Rotation preserves your volume. That is we had actually listed that as rigid body rotation in case of 2D. So, that is done here, right. Okay. Now, suppose we have this, suppose let us say x is a vector with 3 components x1, x2, x3, and let us say I want to rotate this vector x, rotate the vector x by an angle, let us say theta, about the E1 axis. Now, what do we mean by that? You are going to rotate in the plane which is formed by those two vectors E2 and E3 vectors. That means, you are going to rotate about the x2 x3 plane, right. So, what is it going to be? So, I am going to look at r theta. We have already said rotation about the E1 axis. So, I am going to have this. So, what is the vector that I get? I am going to get let us say it is about E1 axis. So, the first row is 1 0 0, the first column is 1 0 0, the second row, second element is cos theta, this is sin theta, and that is minus sin theta and cos theta, right. Now, what I do is we will take simple example, instead of taking one x1, x2, x3 generic case, we will take a simple example where x is equal to let us say 1 2 3. Let us take this to be 1 2 3 and see what basically happens. You can actually fix some values for theta, you can fix some values for theta and see what happens, right. Now, what is r theta E1 of 1 2 3? So, what am I going to get? I am going to have 1 0 0 0 0 cos theta sin theta minus sin theta and cos theta here, and that is going to act on this vector, let us say 1 2 3. So, the resultant we know, the resultant is the first component is fixed. So, nothing happens to the first component. The second component is 2 cos theta minus 3 sin theta, and the third component is 2 sin theta plus 3 cos theta, 2 sin theta plus 3 cos theta, right. Now, what I do is I want to rotate this vector, which is let us say let me call this as r theta of E1, let me call this as let us say the vector u, let me call this as the vector u, the vector u is here. Now, what I do is I now want to rotate this vector u, we want to rotate this vector u about E3 axis. Now, we rotated that about the E1 axis. What we want is we want to rotate this vector about E3 axis, let us see, by an angle phi, by an angle let us say phi. So, what is r phi? R phi about E3 axis. So, let me write this, about E3 axis is my E3 axis is fixed 0 0 1 0 0 1, that means rotation is going to happen in E1 E2 plane. So, I am going to have x1 x2 plane. So, I am going to have cos phi sin phi minus sin phi cos phi, right. And I am going to do let me take this vector v, which is nothing but r phi E 3 of this u vector, the transformation r phi E 3 applied on the u vector. So, what are we going to have? We are going to have this cos phi sin phi 0 minus sin phi cos phi 0 0 0 1, and this is going to be applied on 1. Let us just look at the other vector, 2 cos theta minus 3 sin theta, 2 cos theta minus 3 sin theta, then we are going to have 2 sin theta plus 3 cos theta. Let me erase this. Two cos theta minus 3 sin theta, we have 2 sin theta plus 3 cos theta. Now, let us see what happens. So, this is going to be cos phi plus, if you multiply this, we get cos phi minus sin phi minus sin phi into 2 cos theta minus 3 sin theta. The third component is plus 0 into that, so it is going to be 0. The second component is going to be sin phi plus cos phi into 2 cos theta minus 3 sin theta, plus of course 0 into this, and the third component is going to be 0 0. The third component remains the same, it is not going to change because we are rotating about that axis. So, we have 2 sin theta plus 3 cos theta. So, this is the resultant vector v that we have. Now, what we do, let us look at the other way around. So, what I have, I had the same vector, let me have this vector which we started off initially, we had this vector x which was 1 2 3. So, let me take the same vector. So, I have this vector x which is equal to 1 2 3. Now, what I am going to do is, instead of rotating it by an angle theta in the x2 x3 plane, I will first rotate this by an angle phi in the x1 x2 plane, because that is what we had. So, I am going to rotate x by an angle phi about x3 axis followed by rotation by an angle theta about the x1 axis. So, let us see what happens. So, what was my r phi? R phi is basically rotation about the x3 axis, which means the x3 component is fixed. So, I am going to take it as 0 0 1 0 0 1. I have cos phi sin phi minus sin phi cos phi into, I am going to have 1 2 3, and that is going to give me the following. What is it that I am going to get? I am going to get cos phi minus 2 sin phi, cos phi minus 2 sin phi, then sin phi plus 2 cos phi, and then I am going to get 3. Now, this I am going to do r theta of the above. So, let me call this as my v prime, or this vector u is what I said. So, in the previous case we called this vector as u, I am going to call this as u prime, So, let me call this vector as let us say u prime vector. So, I am going to apply r theta on u prime vector, r theta on u prime, and I am going to get v prime vector. So, what is that? V prime is equal to, what is r theta? Rotation of by an angle theta about x1 axis, which means my x1 component is fixed now. My x2, x3, that is the plane in which I am going to have rotation. So, I have cos theta sin theta minus sin theta cos theta into whatever that we had here, which is cos phi minus 2 sin phi sin phi plus 2 cos phi, and I am going to have 3 here. So, what is the vector that we are going to get? So, I am going to have this vector v prime is equal to excuse me, v prime is equal to, if you see this is cos phi minus 2 sin phi remains the same, cos phi minus 2 sin phi, that remains the same. The second component is, the first component is 0, cos theta into sin phi plus 2 cos phi, cos theta into sin phi plus 2 cos phi plus minus sin theta into 3. So, this is minus 3 sin theta, and this one is again 0, this is sin theta into sin phi plus 2 cos phi, sin theta into sin phi plus 2 cos phi plus 3 cos theta, right, plus 3 cos theta, yeah. Now, this is basically what? This is r phi of about E3 followed by r theta about E1, this is what we had. On the other side, I am going to write r theta about E1 followed by r phi about E3. Let us look at the vector that we had here, which was the vector v. The vector v was the following. We had this cos phi minus sin phi into 2 cos theta minus 3 sin theta. Let us write that cos phi minus sin phi into 2 cos theta minus 3 sin theta sin phi plus cos phi into sin phi plus cos phi into 2 cos theta minus 3 sin theta, and the third one, the third component was 2 sin theta plus 3 cos theta. Now, there is something interesting that happens here. What is that? We see that if you first apply rotation about the E1 axis and then apply rotation about E3 axis, you get a vector v, and if you apply first rotation about E3 axis by an angle phi and then rotation about E1 axis by an angle theta, you get another vector v prime, which are not the same. Whereas in 2D, when we did this r theta followed by r phi and then we did r phi followed by r theta, the resultant vectors were the same, we did not have any problem. Therefore, we said r theta and r phi, the 2 by 2 rotation matrices by an angle theta and by an angle phi, they commute, that means r theta into r phi was equal to r phi into r theta, whereas in this case what we see is if you rotate about one axis first and then do a rotation about another axis, these two rotations do not commute with each other. That means so what we are going to do is r phi about E3 into r theta about E1 is not equal to r phi r theta about E1 into r phi about E3. These two are not the same. That means what we see is we see that there is a problem with rotation in 3 dimension, which was not something which we faced in 2 dimension. We see that the rotation matrices in this case need not commute, especially when you are doing rotations about 2 different axes at 2 different points of time, the rotations will not commute. So, what we are saying in this case, rotation about 2 different axes do not commute, right. So, what we see is there are certain interesting things that happen in 2D and there are much more what do you call, there are certain different things that happen in, let us say, 3 dimension. We saw a few of those things. In 2 dimension we were able to talk only about reflection about a particular line passing through the origin, whereas when we came to 3D we were talking about reflection about a line passing through the origin and about reflection about a plane passing through the origin. That was something new for us in 3 dimension. And again when we looked at rotation, in case of rotation we saw that in 2 dimension the rotation operations were commuting, whereas in this case we see that the rotation does not commute, especially when you try to do successive rotations about different axes. So, this is something new to it. Now, the question that we ask is, are there any more surprises that we are going to get in terms of 3 dimension, like we have seen the in 2 dimension in R2 when we looked at matrix transformations we were looking at determinants, we looked at area of parallelogram, and we looked at in case of 3 dimension we actually looked at volume of a parallelepiped, we also looked at area of parallelogram. So, there were too many interesting things that were happening in 3 dimension. Now, having seen these linear transformations also throwing up some interesting interesting properties, the question is, are there anything more, are there any more surprises that we are going to get, are there any more interesting thing that we are going to have. So, what we will do is in the next lecture we will be focusing purely on determinants of 3 by 3 matrices. We already know, we have found out the determinant, but not exclusively saying that it is the determinant. We will find out the determinant of the matrix and see how do we relate it to the volume of the parallelepiped and what are the properties of determinants. That is something which we will see in the next class. So, we are going to look at what does a determinant mean as far as the 3 by 3 matrix is concerned. So, we are going to look at that in the next class, followed by, like we remember when we did our 2 dimension, we took the case of 2 by 2 transformations, we looked at 2 by 2 matrices for which we had certain fixed directions of vectors. That means these vectors do not get their direction changed upon the application of the transform. Now, we are going to look at the same thing applied in 3D and we are going to look at the idea of eigenvalues and eigenvectors in the subsequent lecture. So, in the next lecture we will look at determinants and properties of the determinants. Thank you.